In this video, we'll look at smaller and smaller objects in a series of steps. We'll start with this oak tree, which is 10 meters tall. Can you see the boy standing underneath? We'll call him Lee, and Lee's height is about 1/10 of the tree's. That makes Lee 1 meter tall. We'll now zoom in using a magnifying power of 10, and that will make Lee's image about the same height as the tree was on the screen before. In this video, we'll continue to find smaller and smaller objects and zoom into them in a series of steps until finally we can see an atom. Now let's find something about 1/10 of Lee's size. The distance between his eyebrows is about right. Let's zoom in to magnify this by 10 so it fills up the screen. Now what's 1/10 of this distance? The width of Lee's iris. That's the coloured part of his eye. His iris is 1/100th of a metre wide. 1/100th of a metre is also called a centimetre. We're going to show you a trick here. 1 on 100 is the same as 1 on 10 squared, because 100 is 10 squared. Scientists often write this as 10 to the negative 2. That's like 10 squared, except that the 2 has a negative in front of it. This negative is telling us that the squaring is on the bottom of the fraction instead of the top. The cool thing is that it's quicker to write it this way, and it gets better. 1 on 1,000 is the same as 1 on 10 cubed, so it can be shortened to 10 to the minus 3. Notice that the 3 corresponds to 3 zeros on the bottom of the fraction. What's 1 over a million? A million's got 6 zeros, so that's 10 to the minus 6. When there are lots more zeros, it gets way quicker to write it this way. We'll show both ways of writing it from now on. Now what's 1/10 of the width of his iris? Hey, did you see the flea that jumped onto Lee's face? Lee's got a flea. Coincidentally, a flea is 1/10 of the width of his iris. That makes it about 1,000th of a metre, or 10 to the negative 3 of a metre. 1,000th of a metre is also called a millimetre. And now the flea is running for cover to Lee's eyebrows. Good move, flea. Let's zoom in. Now we'll flip the angle to show Lee's hair sticking upwards. Guess what's 1/10 of the flea's length? Yep, one of Lee's hairs is 1/10,000th of a metre wide. 4 zeros on the bottom, 10 to the minus 4. This is about the smallest size that the naked human eye can see, and from now on we would need a microscope. If we pan the camera downwards, we can look below Lee's skin and see inside his body. Can you see his blood vessels? If we look inside a blood vessel, we can see that the flowing blood contains red blood cells, and they're about 1/10 of the width of Lee's hair, or 1/100,000th of a metre wide, 10 to the minus 5. They're too small to see without a microscope. Ouch! Here comes an anthrax bacterium, and it's deadly for humans. Luckily, it's rare, and in fact most bacteria are not only not harmful, they're good for you. This one is about 1/10 of the size of a red blood cell, making it 1/1,000,000th of a metre in size, 10 to the negative 6. This length also has its own name, a micrometre. here again is a virus. Most viruses are too small to be seen with a normal microscope, so an electron microscope is needed. A flu virus is 1/10,000,000th of a metre in size. That's 7 zeros on the bottom. 10 to the negative 7. The wavelength of green light is about 5 times the width of this virus. Zooming in another step, we can see that the virus wall, called the envelope, is about 1/10 of the virus width itself, coming in at a staggeringly small 100,000,000th of a metre. That's 10 to the negative 8. The envelope is made out of fats that the virus gets from its host. Yuck! Inside the virus is a strand of DNA, which is its information centre. DNA is a very long but very thin molecule made of billions of atoms joined together. This is the first time we've been able to spot individual atoms. And here comes a sugar molecule, which is a bundle of 45 atoms, about 1/10 of the width of the virus envelope. 1/1000,000th of a metre. 10 to the minus 9 of a metre. Holy dooly! 1/1000th of a metre is also called a nanometre. Heard of nanotechnology? That's about making things that are about a nanometre big. Even tiny robots that can travel around your bloodstream and fix up your body. At this scale, you can see that the whole world is made of atoms. Atoms to the left of you, atoms to the right of you, above and below. This shows you what a grain of sugar might look like, containing trillions of sugar molecules next to each other. But what's between the molecules? More atoms? Air? Well, it can't be air, because air itself is made of atoms. In between molecules is nothing. Zilch. Zip. Just empty space. Scientists call empty space a vacuum. Going back to our nanometre-sized sugar molecule, we can see that the white atoms are about 1/10 of its size. They're hydrogens, and they're about 1/10 of a nanometre, or 10/10,000,000th of a metre across. 10 to the minus 10. That's crazy small. Now we know how big an atom is. What about the other elements? How big are their atoms? A helium atom is about the same as a hydrogen atom, and all the others are bigger. The biggest is cesium, at a whopping 5/10,000,000ths of a metre across. By the way, atoms aren't really coloured like we've shown them here. They're too small even to have colour, because atoms are much smaller even than the wavelength of light. We just gave them different colours so we could tell them apart. So is that it? Are atoms the smallest things in the universe? Not by a long shot. Atoms are made of even smaller particles, called protons, electrons, and neutrons. If we zoom up to a helium atom and look inside it, we find its electrons whizzing around the outside, and its protons and neutrons right in the centre of the atom, called its nucleus. Protons and neutrons are about the same weight as each other, and they're nearly 2,000 times heavier than an electron. That means that most of the mass of an atom is concentrated in its nucleus. We've made the protons and neutrons bigger than they really are here, just so that we can easily see them. but they're really much smaller compared to the overall size of the atom. If you imagine that an atom is as big as a football stadium, then the nucleus would be the size of a pea. In fact, you couldn't even see the protons and neutrons from this distance. We would have to zoom in with a magnification of 10, 5 times, adding another 5 zeros to the bottom of the fraction. That's with 15 zeros on the bottom line. 10 to the negative 15 of a metre. Protons and neutrons are a quadrillionth of a metre wide, also called a femtometre. What's between the electrons and the nucleus? Nothing, a vacuum. That means that an atom is mostly empty space. Since we're made of atoms, so are we. That's enough to do your head in. Anything smaller than a proton or a neutron? You bet. Quarks are a quintillionth of a metre, with 18 zeros on the bottom, also called an attometre. 10 to the negative 18. And neutrinos are a septillionth of a metre, with 24 zeros on the bottom, also called a yoctometre. That's 10 to the negative 24. Did you know that trillions and trillions of neutrinos are passing through your body right now, every second? But don't worry, they're so tiny and light that most miss your atoms completely. That's about as small as it gets. I don't know about you, but I can't imagine stuff that small.
It's hard to imagine just how tiny atoms are. One sheet of paper is roughly 500,000 atoms thick. Volume-wise, one atom is as small compared to an apple as that apple is to the entire Earth. So you might be surprised to learn that chemists can actually see atoms, not with their eyes, with incredibly precise tools. The idea of atoms stretches back to ancient Greece, when the philosopher Democritus declared that all matter is made of tiny particles. The philosopher Plato even decided, wrongly, that different substances had different shaped atoms, like pyramids or cubes. The first modern evidence for atoms appears in the early 1800s, when British chemist John Dalton discovered that chemicals always contain whole number ratios of atoms. That's why it's H2O and not H2.40 or H square root of 17O. The reason for these whole numbers, Dalton suggested, was because you can't have half of an atom or 0.2 atoms, only whole atoms. It's actually kind of hard to imagine chemistry today without Dalton's insight, but it was controversial during its day. Why? Because chemists couldn't see atoms. Many considered them like negative numbers, useful for calculating things, but not existing in the real world. Even Dmitri Mendeleev, father of the periodic table, refused to believe in atoms for many years. So why didn't chemists just look for atoms under microscopes? To see something under a microscope, the wavelength of light you're shining through the microscope can't be larger than whatever you're looking at. Unfortunately, visible light is thousands of times bigger than atoms. So chemists had to wait for light with short wavelengths, like X-rays. X-rays were discovered in the 1890s by German scientist Wilhelm Röntgen, who realized that photographs taken with X-rays allowed him to see through objects. Röntgen thought he'd gone insane when he saw this, but today we're all familiar with X-rays from trips to the dentist and doctor. Chemists don't use X-rays to see through things, however. Instead, they bounce X-rays off things like crystals, which are solids with layers of atoms. When X-rays hit an atom in the crystal, they bounce back. Others slip through and bounce off the second layer down, or the third layer, or deeper. After being reflected, these X-rays strike a detector screen, like the ball bouncing back in Pong. And based on the pattern of where they strike the wall, scientists can work backward and figure out the 3D arrangement of atoms in the crystal. This reflection and interaction of light rays is called diffraction. X-ray diffraction, sometimes called X-ray crystallography, has led to dozens of Nobel Prizes for chemists since the 1920s. It also led to one of the biggest discoveries in science history, the structure of DNA. James Watson and Francis Crick get credit nowadays, but they based their work on the work of Rosalind Franklin, a crystallographer in England. She began taking X-ray pictures of DNA in 1952, and Watson's glimpse of one picture, photograph 51, was a vital clue in determining that DNA was a double helix. This incident actually remains controversial today because Franklin never gave Watson permission to view photograph 51. If X-rays let chemists peer at the structure of atoms, scanning tunneling microscopes finally revealed the atoms themselves. Rather than bounce light off something, an STM runs a sharp needle over the surface. It's like chemical braille, except the tip never quite touches. As the tip moves along the surface, scientists can reconstruct the atomic landscape, making individual atoms visible at last in the early 1980s. Lo and behold, the atoms weren't Plato's cubes and pyramids, but spheres of different sizes. By 1989, a few scientists had even adapted STM technology to manipulate xenon atoms and spell out words. We'll let you guess what company they worked for. Also in 1989, the chemist Ahmed Zewail moved beyond looking at stationary atoms and developed tools to see atoms in action. Zewail wanted to study how atoms break bonds and swap partners during reactions. So he developed the world's fastest camera, which shoots pulses of laser light a few femtoseconds long, a few billionths of a microsecond. While Zewail's laser flashed like a strobe, his camera snapped pictures. Zewail then ran the pictures together like a slow-motion replay. Since then, femtochemistry has provided insight into everything from ozone depletion to the working of the human retina. Zewail won a Nobel Prize for his work in chemistry in 1999. The ancient Greeks dreamed up fanciful shapes for atoms, but it took 2,400 years before scientists could see them for real and study their behavior. Seeing truly is believing for human beings, and it was chemists and other scientists who fulfilled this need and finally revealed what our universe is made of.
When we study science, it's natural to just categorize a whole series of things as just being really, really unimaginably small. So when people say, hey, atomic scale or molecular scale or protein or a cell, you often just group that together and say, oh, those are really, 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 really small things. But what I want to do in this video is get an appreciation that even though all the things I just mentioned are really small, there's actually a huge difference in the sizes of those things. And hopefully that'll give us an appreciation for how complex something like a cell can be, how it can have all of this machinery, how it can actually be a living organism or part of a living organism. And so at this scale, this is my little rendering, my drawing of a water molecule. You have the oxygen atom in the right over here in this purplish color, and then you have two hydrogen molecules bonded to it. And this is going to be roughly 0.275 nanometers. And just to remind ourselves, a nanometer is a billionth of a meter. And just to get an appreciation of that, so this is 1 billionth of a meter. That's a nanometer. And if you want to even attempt to visualize that, that would be a millionth of a millimeter. So let me write this, 1 millionth of a millimeter. And I actually like using this one because a millimeter is about as small as I can on a reasonable basis visualize. But it's in a millionth of that. So this definitely goes well beyond at least my capabilities of visualization. So that would be the diameter or the width of a water molecule. But now let's go to the next scale up. We've talked a lot about proteins, and this is our friend, this right over here is our friend hemoglobin. And just so you get a sense of scale, the width of hemoglobin is going to be about 5 nanometers, or 5 billionths of a meter. Now that seems super small, so in some ways it's okay to categorize that into your super small part of the brain, but it's good to appreciate this is much larger than a water molecule. If a water molecule were on this scale, I pre-drew it, this little thing over here, that's my attempt at drawing a water molecule at this same scale. So even when you go from something like a water molecule to a protein, you're already going dramatically up in size and dramatically up in complexity. And we've talked a lot about protein structure, how they can take on all these interesting shapes and do fairly surprising and complex things inside of biological systems. But now let's go the next scale up. And the next scale up, I'm going to go to a virus. And what I've attempted to draw here, this is a fairly well-known virus. This is HIV, and it's actually one of the larger viruses, and its diameter is roughly 120 nanometers. So if we were to draw this hemoglobin protein at the same scale as we've drawn this virus, this thing right over here would be the hemoglobin protein, and we wouldn't even be able to see the water molecule at this scale right over here. But this is still really, really small. This is 120 billionths of a meter. So this is still unimaginably small. But now let's go up to the next scale. So this creepy picture right over here, this is a T cell. This is a depiction. This is if you want to see the whole thing, that is a T cell right over here. This is a T cell, and this creepy picture, all the blue, that's the T cell, and what you see in yellow, that's the HIV virus emerging, taking advantage of this T cell. So that's why it's so creepy. It's using that cell's machinery to reproduce itself. But you immediately see on this picture how small the HIV virus is compared to the actual T cell. Each of these small little things is an HIV virus, which we already saw is a lot bigger than something like a hemoglobin protein. And so hemoglobin protein, you wouldn't even be able to, on this scale, maybe it would be a pixel, if that. And on a similar scale as this T cell, you have things like red blood cells, and this is actually a comparison, side by side. This is using an electron. This is using an electron microscope. You see a red blood cell right over here, and you see a T cell, and they're roughly on the same size, or at least the same order of magnitude size. And a red blood cell is going to be 6 to 8 micrometers wide. So this is 6 to 8 millionths of a meter. So if we were to just take 7 as the average, 7 millionths of a meter. Over here we're talking about a millionth of a millimeter. Now we're talking about 7 millionths of a meter. And just to get an appreciation for size, we already compared the virus, the HIV virus, to this cell. We're seeing it directly as they emerge from this cell. But each of these red blood cells are going to contain roughly 280 million hemoglobin molecules. So there's going to be 200, each of these, there's going to be 280 million of these. So 280 million, that's not million hemoglobins in each one of these. So hopefully this starts to give you an appreciation for, even though we categorize cells as these unimaginably small things, they're actually far larger. They're ginormous compared to things even like large, even proteins, and especially when you think of things on the molecular or the atomic scale. And that's why cells are so interesting. They actually have a lot of complexity to them. But just to have an appreciation also for how small cells are, even though we've just described these red blood cells and these T cells, there's these, they're these kind of worlds unto themselves. They're these incredibly complex things. If I were to draw the width of a human hair on this screen right now, relative to the scale of these red blood cells, it would be about as wide as this video. So if I were to draw a human hair, it would go from there roughly to there. And there's actually a lot of variance in the width of a human hair. But the width of a human hair would be just about like that. If you looked at the scale of this picture right over here, if you looked at these scales, then it would be much, 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 much bigger. And I encourage you, we can think, oh, okay, width of a human hair. Pluck a hair out, look at it, put it on a piece of paper. It's hard to even discern the width, but we're saying that width compared to these red blood cells would actually be the entire width of the screen. And we've already said these red blood cells, these C cells, these are worlds unto themselves when you think of it from a viral or especially at a molecular scale.
Our universe, a vast and mystical place, yet full of mystery. How big is it? Why are we here? Is there a higher being up there? To answer these, we first got to look deep within ourselves, really deep, to what makes us, and ultimately, the universe. At the universal domain of tininess, these are quantum foams atop one-dimension strings, the fabric of space-time itself, going any smaller would defy the laws of physics. This is the smallest thing in existence, a Planck particle. The next smallest thing are quintillion times bigger. Everything in our universe are made up of these particles defined by the standard model. They are responsible for mass, electromagnetism, gravity, and radioactive decay. The smallest of them is the electron neutrino, so small it weighs against even the smallest quark. These are quarks which combine to form composite particles, the most familiar being the protons and neutrons. This wave is from the photon, the light particle. Zooming further, we pass by electrons and reach the Higgs boson, the particle responsible for mass. And finally, we made it to what we're all familiar with, protons and neutrons, some of which combine to form atomic nucleus, the largest being element 118. Yet, the nucleus is a tiny fraction of the atom. Electrons in quantum motion orbits this vast empty space, and at last, the atom. Big, huh? Our body alone is made up of 1 octillion atoms, with cesium being the largest. Some of these bond to form the 4 building blocks of life: proteins, carbohydrates, fats, and DNA. The wonders of nanotechnology exist here. This is a clickable view of an electron microscope. The land here is ruled by viruses, so small yet deadly. For example, HIV claims millions annually. We zoom out to bacteria. Our body alone has an astonishing 100 trillion of them. These are cells that makes up life. Every single one of our 40 trillion cells contains 20 billion pairs of DNA genome. We reach the landscape of some of the smallest animals. At this scale, even a flea looks like something straight off a horror movie. Ugh. A rice grain and an ant. We're getting more familiar. Oh, would you look at that genius channel advertisement on the iPhone? And here's your daily dose of nightmare. Enjoy. Do be grateful they didn't grow as big as us. And this is where we stand, created by the very laws of the microscopic world, to create the vast macroscopic world beyond us. Marvel of the fascinations of the animal kingdom, and its biggest land mammal, the elephant. Yet, the ocean dwells even larger creatures. For example, the giant squid, the Jurassic World mosasaur, and a blue whale, the largest animal ever existed. But history produced even greater creatures, a jet-sized flying creature, a dinosaur longer than a blue whale, and another taller than a 5-story building. Still dwarf in comparison to the tallest living organism, the Hyperion tree. But we scale higher with aerodynamic technology. And behold, the largest thing to ever flew the skies, the Hindenburg. We have also conquered the seas with naval technology. Behold, the Poseidon of the sea, Yael Viking. And we've reached higher than ever, building architectural masterpieces towering city skylines, even exceeding natural wonders. We've not only exceeded vertically, but horizontally as well. Yet nature always outdoes us, forming landforms reaching incredible heights. But our species spread wide and far. Yet space is a whole new frontier. These are the moons of other planets, vast areas of unexplored regions, climate, and landscape awaits. As we zoom out from moons to planets, we ask ourselves, where are we? That's here. That's Earth. On it, everyone you ever know, every religion, every ideology, every conflict, every experience, every saint and sinner in history of our species live out their lives in a speck of dust, suspended in space. The sun, a ball of superheated gas, can fit 1 million Earth inside of it, yet our sun is tiny compared to the really big stars out there. Polaris, over 10,000 times bigger than our sun. Pistol star, 3,000 times larger than Polaris. If it was our sun, it would have reached far out as Mars. And then there's this monster, Scusi, the largest star ever discovered, 1 billion times bigger than our sun. The extent of our solar system. Yet, it's just one of many solar systems in our galaxy, one of them being the TRAPPIST-1 star system, believed to house 7 planets with life. Passing by Sednar orbit, witness the largest black hole and abyss among these interstellar beauties. We've reached the distance light travels in a year, just reaching the nearest stars. At this scale, a space shuttle would take hundreds of millions of years to cover. These spectacular objects you see are called nebulas. There are interstellar regions of clouds and stardust, the largest and probably most boring named one being this, NGC 604. But they are accompanied by stars, lots of them. Some have dozens of planets. As we traverse our Milky Way, could there be someone, somewhere out there, among billions of stars and trillions of planets, thinking, do we exist? Our Milky Way, home to 100 billion stars, our sun being just one of them, is just one of trillions of galaxies out there, each with billions of stars. And some are really, really big. IC 1101, the largest galaxy. It contains 100 trillion stars and 1 quadrillion planets. Could there be one with life? Galaxies merge to form galaxy clusters. Each speck you see here is not a single star, but a whole galaxy of stars, seen as one. Laniakea, a supercluster of 100,000 galaxies. In just one of many superclusters in the Physis-Cetus supercluster complex, with many other supercluster complex, form the vast cosmic web. And eventually, our universe. Here lies everything. Or does it? What if there's a universe, one where Hillary Clinton became president, one where Hitler won the war, or the dinosaur never went extinct? What if there are parallel universes with different timelines? How many would there be? A lot. In just 1 second, anything could happen. This is the number of parallel universes in the next second alone. A number so big it's just the number of digits it have. Anything from your crush texting you now to this video hangs happens here. Yet, since the Big Bang, unimaginable numbers of parallel universes have formed. Every possible event imaginable, every alternate timeline conceivable. Everything within the laws of physics, every possible outcome throughout all of space-time itself exists here. Parallel universe. Yet, could there even be other parallel universes with different laws of physics, other dimensions, and even colors we can't see? Alternate universe with everything we can't ever imagine nor comprehend. The multiverse.